In topic 4, we're looking at functions. This is a very important concept in math, and I have some background material, again, over on the left of your booklet. You should write these notes. So we're going to look at what is called a relation in mathematics. And if you're familiar with what is called the ordered pair, when we do a graph and we plot, let's say, the numbers 2, 3, we go on our x-axis and we go over 2, doing the x element first, 1, 2, and then we go up 3 and we put a dot there. So you would definitely say that these two numbers are connected. That is, make up a relation in mathematics. Now, another important word is the word domain. Domain refers to the x elements, or items that would go along the x-axis, the horizontal axis. That's what makes up the domain, the x elements. Now, the range are those elements that go along the y-axis, that is the vertical axis. So again, you need to be familiar with relation, domain, and range. Now, in mathematics, many things could be a relation, but in order to be considered a function, the x element, that is the items that go along the x-axis, can only be used once in a series of relations. And we'll give you examples of this as we go on. Now, some other background material that you may or may not have brought in from other math courses is what we call roster notation. In roster notation, we just list items that are included in the set, and usually we're talking about sets of numbers. For instance, if we said the set of numbers between 1 and 5, well, that would be, we'd put like a brace, and between 1 and 5 would be 2, 3, 4, and then we close it with a brace. So this would be roster notation, where we're listing the elements. Now, set builder notation has a brace also, and let's say we said the set of numbers in the real number system. Well, we'd say x is such that x is a real number, and we close it. Now, this would be set builder notation. It's set up in this pattern. Now, there's more detail of this, of course, in your textbook, but this is an outline. Now, interval notation, and I perhaps should say, if we had a number line and we were going to plot all real numbers on this number line, it would look like so. And usually, if we had a blank number line, imagine this a blank number line, and 0 is here in the middle, and we just darken it and then we put our arrows to indicate it goes on in both directions now. This would be the graph of all real numbers. Now, how would we write this in interval notation? Well, there is a protocol for this, and we would start with saying, where is this coming from? Well, out here is negative infinity, and out in this direction is positive infinity. So in interval notation, we start with a parenthesis or a bracket, and I'll go over that when we get to it a little later. But we put negative infinity, a comma, and it goes now to positive infinity. And infinity always has a parenthesis closing it. So from negative infinity to positive infinity, the graph. This is interval notation. Just to give you a little background on the vocabulary. Okay, so again, you have some notes on this because we'll be referring to this. One of the things students sometimes have a problem with is they know the words domain and range, but they're not sure whether it refers to the X or the Y. Now, if we put domain and range alphabetically, as we have here, D comes before R, and we put the letters X and Y alphabetically, this is what is a good way to remember them. Domain is the X, range is the Y. Alphabetically, alphabetically. A little hint. Okay, we're going to go now and start looking at specific examples. This was the background of what we need to do these examples. Now, as we look at this, and this is often the kind of thing they ask you, is this a function? Now, a synonym for relation is a correspondence. Something corresponds to something or is related. Now, are these a function? Well, again, the first column here we can think as the X elements, and the second column here we can think as the Y elements. Now, in a function, the X element is only used once. So we look at the 5. Corresponds with the 28. The 6 corresponds with the 30. 8 corresponds with the 30. So are the X elements here only used once, or a way of looking at it, is there only one arrow coming from each of the X elements? And the answer is yes. So this is a function. The X element's only used once. Now, sometimes as you read it, you may not understand it that well, but let's look at it. The correspondence matching the numbers with each number's cube. So it would be 5 corresponding to 5 cubed, 6 corresponding to 6 cubed, 7, 8, and now we've made a picture of it to help us better understand it, are the X elements, which is the first column, only used once in regard to the second column, the Y elements? And the answer is yes. So this also is, I guess I have too many I's there. So this correspondence is a function. Now, let me clear this, and I'm going to just change one thing. I'm going to say that this 5 here now, I'm going to put another arrow. Now that wasn't there originally. I'm putting this extra arrow in. So here we have the 5 going with the 28 and the 5 going with the 30 also. So would this, in this condition, be a function? Well, the 5 is used twice. So then in this condition, this would not be a function. Okay? Let's go on. So we see in this slide a series of ordered pairs. It's sort of in roster notation. And we're asked to define the domain. So I'll put a D here. We're also asked to find the range. I'll put an R there. And determine if it's a function. Well, in doing this, again, we use a brace, and we just list the x elements. So a -3, put a comma to separate them. Now notice -3 here as an x element is repeated. Now when we write it in roster notation, we only write it once. It's repeated. And since it is repeated, this will not be a function. We can do that part. And then 0 and 4. Now for the range, 4, 5, 9, 11. Now we notice the range elements, the y's, are not repeated, but we don't really care about that. It's the x element being repeated that makes this not a function. And in here, setting it up the same way, and this is what we'd like you to show in your notes. Brace 0, 1, 2, 4. -6, 0, 3, 10. Now, are the x elements repeated? No. So yes, this is a function. Just putting that for stress. It's not part of the mathematical symbols. Actually, the exclamation mark is, but we don't use it in this course. All right, let's go on. Now, in this example, this is called a piecewise graph, where you have pieces of one line and pieces of another line. They're asking us to determine the domain, so we'll put a D there. They're asking us if we have this function, f of x, where y is 2, because we can take this function symbol and substitute a y there. And we'll go over how to do these. We'll just set it up. And then we want to know the range. And we'll set this one up too. Domain f of x, which we said is a y, equals 2, and then the range. All right, well, let's study this here. So what is the domain of this? Well, this line continues off, and I'm just modifying it to show you its general direction, is going to go in this direction, and we'll end up here in -infinity on this end. And this line continues in this direction eventually, and we'll go to positive infinity. And actually, I don't need to put parentheses yet. Now notice as it gets to this point here, which is like a -1, there's a hollow. So -1 is not in this one. But as we look up here, this is a darkened spot indicating that -1 is there. So in a sense, there is an unbroken line here from -infinity to +infinity. So how would we indicate the domain? Well, it would be all real numbers going from -infinity to +infinity, but we put that then in interval notation. Here's where we use the parenthesis, -infinity to +infinity. Now it's critical that you're taking some notes on this and you're seeing how we write it. So again, because of the solid dot there, this would be a hollow. Now, a question that they're not asking us here is the domain for this particular graph a function? Well, if this were a solid dot, then the -1 value of x would be used twice. Since it's a hollow dot, this graph is of a function. Now, in looking at f of x is equal to 2, or our y value is 2, they're asking what would the x value be? Well, let's look at this. Where is y on this graph 2? Well, it's right there. Y is 2 right there. Now, what is the x value when y is 2? Well, it's right there, and it is a +1. So that's not really tricky, but it's being able to understand what they're asking us here. F of x can be substituted with the letter y. So they're saying here y is equal to 2. Well, 0, 1, 2. There's your y value. Well, what is the x value there? And it's a +1. Now this point here would be written 1, 2. That is, you would go over 1 and up 2. So when y is 2, our x value is 1. Now, what's the range of this? Here's where it gets a little tricky. These would be y values. Notice the line stops here, and our y value of this line right there is 6. So the range is coming up here. In this sense, we're looking coming up this way from -infinity. That's what's down here, because this is an arrow, and this is an arrow that's going down here, -infinity, coming up, going through these points, and it stops at 6. And when we have a definitive point, a definite point that it stops at, and that is included in the set, we don't use a parenthesis, we use a bracket. So this is interval notation for the range of letter A. Again, lots of stuff going on here. All right, let's take a look at letter B. And for a math star, does anyone know what this is like, this kind of curve here? Well, that would be that f of x is like the square root of x plus 1. That would be the actual graph of this. This is something we're going to do later in the course, but they've given us this right now. Anyway. Okay, so my question is, what is the domain of this? And we want to put it in interval notation. Well, we reflect this down to the x-axis. There's a dot. So if we were to graph this on a number line, this would be 0. This would be a -1. So we'd put a -1 there. And to graph this, because our -1 is included in the set, we would use a bracket at -1. And then it goes on to infinity in the x direction here. So we darken all this. Now we want to convert this as our domain into interval notation. Interval notation is very closely related to the graph of this. So it actually is going to start, put a bracket at -1, and it's going to positive infinity. Now infinity always has a parenthesis because we don't know the number it's there. It just continues. All right, now when f of x is equal to 2, that is y equals 2, what will our x value be here? Well, y is 2 right there. What is our x value at this point? Think about it, and the answer is 0. So that's this answer. Now, how about the range? Range are y values. And again, reflect this over to the y-axis. What number is right there? And it is included. And that's a 1. And this eventually will go up to where? Positive infinity. So lots of math stuff going on here. Be sure you have some notes, and remember you can always watch this video again, forward it, fast forward it, go back, whatever. Try to understand what's going on, and have a blank page, and then you do it. See if you can get the information. And I see I'm missing this. F of 3. So this is our x value. Here we're going to wonder what is our y value. So now that you see how it's done, maybe a little easier. So here our x is 3. So 1, 2, 3, right there. What is our y value going to be? And the answer is -2. So this ordered pair here would be 3, -2. So if x is 3, our y value is -2. And let's see this one. If x is 3, so x is 3 is 1, 2, 3 right here. This would be our y value, 1, 2, 3. Our y value there is 3. And this ordered pair would be 3, 3. So we have our x value. then that equals our y value, which is 3. Okay, I missed that when I set that up. All right, let's go on. Now, in doing example 3, a good strategy would be to set up what we call a little t-chart, where we put our x and our f of n up in the top, and then our values for x there and there. Now, what we're going to do is substitute in this, putting a 3. So n plus 6 would be 3, substituting for the n, plus 6. That just gives you a 9. And then now we're going to substitute for the n, this. So that becomes x plus 1, which is what our n is, plus 6, which is this part. So this just becomes x plus 7. So again, as long as you understand or work on understanding how you do the substitution and a way to set it up to show your results. Now here, again, I've set up a little chart where we're going to put a 1 where the a is, and let's just do that. So this will be 1 minus 3, putting the 1 where the a is, over 2 times 1, which is 2, plus 1. So when we do the substitution, we end up with a negative 2/3 for this value. And then when we put a 3 in there, we're going to get 3 minus 3 on top. And then 2 times 3 is 6, plus 1 is 7. And this will give us a 0 over 7. Now, if you put a 0 over 7 as your answer here, even though that's what you got, that would be considered incorrect. And you might say, why is that? Because you haven't simplified this. 0 divided by any real number other than 0 is 0. So here you have to put a 0. If you put 0 over 7 in MATLAB, they're going to count it wrong. Now, in your booklet, if you've written this, and you just failed to put the 0 there as you simplify this, I can give you partial credit. And if that were a test item on your final exam, again, you're showing the work, the steps, I could give you partial credit for it. Because you did all the correct things, you just didn't simplify correctly. Let's go on. Now, hidden in this next examples, or series of examples, are how do we determine the domain of a function? And these are all written in function notation. Well, the key to any of these is if you have a denominator in which there is a letter, let's say x plus 2, as an example. Here we have 2x minus 8, so we'll get to that. Any situation in which there is a variable in the denominator, in order to define a domain, we can never have something divided by 0. This in mathematics is undefined. So, any value of x that would make the denominator a 0 has to be excluded from the domain. So here, is there any variable in the denominator? No. So the domain of this would be all real numbers. And we can use that symbol for that. Is there a variable in this denominator? No. So these are all real numbers. Is there a variable in this denominator? Now it has a denominator other than 1. Every number is over 1. We just don't write it. And the answer is, it has a 9 there, but it has no variable. So the domain is all real numbers. But now as we look at this one, and this is just a made-up one, is there a variable in this denominator? And the answer is yes. Well, what value of x would make this denominator a 0? And the way to do it is you just equal the denominator to 0 and solve this little equation. X is equal to -2. So this is the value that if we put a -2 in the denominator for x would make this denominator a 0. So what would be the domain of this one here, just as a practice one? Well, in set builder notation, we say the domain is such that x is all real numbers, but x cannot equal a -2. Why? Because if it were a -2, it would make our denominator a 0. So in this example, and again this is just a practice example, that would be the number of x that would be excluded. Now if we made a graph of this, which is going to be useful too, and this would be a -2, we'd have to put a hollow over -2, and that would be the graph of the domain of this set builder notation and of this value here. We'll get to that one in a moment. Now, what would be interval notation of this? Well, again, take some notes on this because this is useful. It would come from -infinity and it would go up to -2. But -2 is not included, so we put a parenthesis there. And a little later we're going to have more of this. We use this symbol that we haven't had yet. It's called union. And then on the other side starts at -2 and goes to positive infinity. Okay, background. Now, how about this? Well, we're going to equal it to 0. And we get 2x transpose the 8. On this side it becomes a positive 8. Divide by 2. X equals 4. So 4 is the excluded value in this domain of this particular example. So we're going to say in set builder notation that x is such that x is, we can use the symbol all real numbers, but cannot be 4. Now, often they'll give you multiple choice. You just have to pick out the answer. But we are reviewing for something coming up where we're going to deal with interval notation and graphing and set builder notation. Let's go on. Now, take a moment as we look at this, and some of this is a little bit complicated. So we're going to make a t-chart to display our data, and we have here that one of these is f of x is x plus 4. So I put that x plus 4 there, and they give us this restriction that x is less than or equal to 0. Now, of these two values, -4 and a +1, what number will I put here for x? That x is less than or equal to 0. Well, we don't put both numbers because the only one that qualifies here is the -4. Now, for this second part where we have 4x, if x is greater than 0, which values apply there? Just the 1. Okay. So we had qualifiers. We have this function. And by the way, this is called piecewise. We had the graph of this in 2a that was similar to this. So if x is a -4, what will y be here? Well, 4, a -4, which is our x value, plus 4 is going to be a 0. So the answer to this first part is 0. Now for this one, it's going to be x is 1. So 4 times 1 is 4. So in looking at this, part of it was to understand what's there and then have a way to display it. All right, let's set this next one up in a similar way. Now in this pieces of things, piecewise functions, we have g of x. X squared is this, 3x squared is this function. Notice this restriction, it's less than -4, and here it's greater or equal to -4, and our values are -4 and a 1. Well, in this first one, neither of these values fit within this restriction. So there's nothing to do here. Now, when we look at this second one, it's greater or equal to -4, yes, that would be okay. And then it's 1, that would be okay too. So we then take in a substitution of this, 3, -4 squared. Well, -4 squared is 16, and 3 times, that's a positive 16, 3 times 16 is 48. So that's the answer to this one. And if we put in there 3 times 1 squared, 1 squared is 1, times 3 is 3. So again, there were lots of stuff in this one lesson. We gave you some background. We showed you a number of things. And, there'll be other things too that you may not know. Bring those questions in. We'll have a few examples in other things in class. And of course, as you have your practice, you don't know something, bring that into lab or to me. Between classes, I'm very happy to help you out.